All right, we're going to look at what's called the Lagrange error bound for Taylor polynomials today. So if we say that P of n is our nth order Taylor polynomial. So remember, Taylor polynomials can be used to approximate if you're doing it from the first term through infinity. In theory, it should be the same as the function. If we only do it to the nth term, it should approximate the graph around this C pretty good, but it won't be the exact same as whatever that function is, f of x. But how we calculate it out again is this Taylor function here, where you take the certain derivative at the value C over the k, whatever that same k factorial is, to the k power, again around x minus c. And if you do it out here, they're showing some terms here. But what we're going to look at is what is that error? What's the difference between p of n, which would be given by this function here, and the actual function that it's trying to replicate? There's going to be some error in there. What we mean by that is if you look at the picture here, if we have some function, and here it looks like our function is the sine function. So here's the sine function. So in this case, that would be our f of x. And we've seen this function before on previous videos. And then here is some p of n here that is trying to approximate that. And it looks like it might be a Maclaurin one here centered at 0. So the red one, that's our p of x here for some number of values. What we're looking for is around some value out here. What's that r? What's the error involved? How much different is it here than it should be right here? And that's the value that we're seeking out to get today. That's the Lagrange error. So how do we calculate this error? What we're looking for is this right here, Lagrange error bound. And you calculate it by taking m, and we'll talk about what m is, over the n plus 1 factorial. So we want the term up, the n plus 1 term up. So whatever n is that we're using to approximate it, however many terms out, we're using the next one. And here's our x minus c. So c is what it's centered around, but we want to use that n plus 1 again. And then our m value is the absolute value, okay, absolute value of the n plus 1 derivative at z, where z can be any value between our c value and the value that we're looking at. So any value between x and c. So we want what's the biggest the derivative could be on that interval, and that is our m. It sounds complicated, but in practice, there's usually a pretty quick way to decide what m should be, and we'll look at it here in an example next. So here's kind of that same formula again. So r sub n, that's our r sub n of x, that's our error over here. When we're doing this, our m value, what we saw, it's going to be that n plus 1. What's the what can that derivative be the biggest on that interval? Okay, and then we use absolute value to keep things positive when we're calculating the error with that. Okay, so same thing, just written a little bit different. All right, so here's an example. Use Lagrange error to estimate the error in using a 4th degree Maclaurin polynomial to approximate cosine of pi over 4. Okay, so let's figure out first cosine pi over 4. We've seen that before. If you're looking at uh, unit circle. Okay, pi over 4 is the same as 45 degrees. So if we're looking at that here, that means that this side would be square root 2 over 2, and this is also square root 2 over 2. So cosine, which is the adjacent side, cosine of pi over 4, the exact value of that, square root 2 over 2, if you approximate that out, which we're going to want here. Let's hop on a calculator and approximate that out. Cosine of pi over 4. We can see the approximate value is about 7 or 0.707. We'll go a couple more decimal places, 106. All right, so there's it's approximated out a little bit. What we're going to do is try to find what is that Taylor series that approximates the cosine pi over 4 function. And since it says Maclaurin, we know that it's centered at 0 here. So when we're doing this, our value here, depending on what you want to use, some of the things used A, some use C, but we'll use C here. Okay, so we know what we're going to need to do here is for some different values of n, and they said to use a 4th degree one here. So we're going to calculate this out. I'm going to actually go one past that to the 5th. And we're going to want to find this function at different values of this. And since it's a Maclaurin one again, we want to figure out what is this centered at 0 then. Okay, so the original function here would be just its cosine of x. So cosine of x. And if you do cosine at 0 here, that should equal 1. All right, what's the derivative of cosine? That should be negative sine. What is negative sine at 0? That should be 0. Next derivative would be negative cosine. What is negative cosine of 0? That should be negative 1. Next derivative would be positive sine. And sine of 0 ends up being 0. Next derivative is cosine. Cosine 0, we've had that one before. That's 1. And I'm going to go one more here. Negative sine and derivative. Or sorry, negative sine evaluated at 0. We've had that one before as well. That's 0. Okay, so there's the different derivatives there. Next thing, what is the approximation? Well, let's find out what that P of 4 is. So remember to find these out. Our way of finding Taylor polynomials is to do the summation here, and we're going to go from 0 to 4 here of our derivative at n over n factorial and x minus whatever our c value is here to the n. And actually, I probably should have the same thing here. So we're finding it at that same value. And here it's 0 because we're doing a Maclaurin one. So if we fill this in, first one, if we put n equals 0 in there, the value we're going to get on top is 1 over 0 factorial. Here we get x minus 0 to the 0 power, which all of that should just end up equaling 1 here. All right, our next term is the first power. So now we got 0 would be our top, our derivative here at that over 1 factorial x minus 0 to the first, but because there's a 0 there, it doesn't matter. All that's just going to be equal to 0. Our next one, we're now putting in our next value down, which would be -1 over 2 factorial x minus 0 squared, which when we simplify that one should be, looks like x squared over 2 factorial, which is just 2. All right, next one, our coefficient is 0, so I'm not going to bother writing all that out, but this next one's going to be 0. And our last one, now we're on the fourth one here, so we're going to have our fourth derivative value 1 over 4 factorial, x minus 0 to the fourth. So that's going to give us positive x to the fourth over 4 factorial, which is 4 times 3 times 2 times 1, which is going to come out to be 24. So there's our Maclaurin Taylor polynomial centered at 0 that can be used to approximate cosine. So what they want us to do now is figure out what's the error in using this to approximate cosine pi over 4. Let's first see what value we get here. So if we take this and use it to approximate at pi over 4, what are we going to get? So that means putting pi over 4 in for these x values and seeing what does this come out to be. So we'll use our calculator to evaluate that. And it should give us something hopefully fairly close to what we got up here. So let's pop that in a calculator and see what we get. So on our calculator, we're going to go 1 minus pi over 4 squared, and we want to divide that by 2 plus, and we got, whoop, I wrote the wrong number here. This should be to the fourth power here. So we got pi over 4 to the fourth power, and we want to divide this one by 24. And if we do that, here's our approximation. You can see fairly similar here. This one, that approximation comes out to be 0.707. So to the first 3 decimal points, it's the same. Here's now where we start going off. It's like 429 here. So up to 3 decimal places, fairly close. They want us to use the Lagrange error bound now, okay, to estimate that error. So what's the error between the approximation that we got down here and the actual value that we see here? So to do that, we're going to use our Lagrange error here. So Lagrange error that we saw on the previous slides here is that the error, or most things use R here, so R of 4 here of x is going to be, and we're going to use absolute value here, less than or equal to our m value over the n plus 1 term, factorial, times x minus 0. And actually, I'm going to go back here. We want to use, since we're doing absolute value here, we want to use absolute value. Absolute value to the n plus 1 power. Okay, so since we're doing 4 here as our n, we want to fill in both of these with 4. So this will be to the 4 plus 1 factorial. This is just going to be end up being x here to the 4 plus 1 power, which we know is both going to come out to be 5. So 5 factorial and x to the 5th power. Okay. The other thing we got to calculate out is what is m. So the m value, how we factor or calculate m, is that our m value, pick a different color here, that one's hard to see. Our m value is the absolute value of f to the n plus 1 power here at pi on the region, I should say from uh, where this is z, and we'll talk about what z is here. Um, what's that going to come out to be? Well, here, if we're using 4, that means our m here is going to be the absolute value of the fifth derivative of this on z, where z can be anything between, or on the interval from 0, because we're doing a Maclaurin one, to our value of pi over 4. So what's the biggest the fifth derivative can be from 0 to pi over 4, the absolute value of that? Well, if we go back up, our fifth derivative here ends up being negative sine x. Okay, so that's our fifth derivative. So we want to know for this one, what's the biggest that negative sine x can be on that interval z. So if we look at the graph of negative sine x, so I've entered negative sine x, here's the, let's graph that out. Here's our negative sine graph. What's the biggest value that can be from 0 to pi over 4? Well, pi over 4 is right halfway in between there. That looks like the biggest value it could be because we're taking the absolute value of that. At 0, the value is going to be 0. The biggest it can be is at pi over 4. So our m value for this one is going to be the absolute value of negative sine x at pi over 4. And just like cosine of pi over 4 is square root 2 over 2, this should also come out to be square root 2 over 2. So it'll come out to be negative square root 2 over 2, which since we're doing the absolute value is going to come out to be square root 2 over 2. So that's the m value that we want to use here. All right, so now we got everything we need here. So we're going to now calculate this out. And since we're doing it at pi over 4, our x value on this one is going to end up being pi over 4. An absolute value that's positive, so it'd be positive pi over 4 to the fifth power. So we want to now enter that in our calculator, and that should be the biggest that the error is going to be. So on our calculator, we're going to plug that in and see what we get. So get out of here, go to our main screen here. All right, so we want to enter that in. So we got square root of 2 over 2. That value times pi over 4 to the fifth power. So we want to take all that, and then we want to divide it by 5 factorial. So divided by 5. And in your math menu, if you go to the probability, you can find that factorial key. So the error on this one should be within or less than 0.00176. So our error should be less than or equal to this value. So that is our error coefficient, which means it should be within 0.1 in the thousandth place. And you can see from our two answers here that we were definitely within 0.1 in the thousandth place. In fact, we had the same value there in the thousandth place. But we're guaranteed accuracy out to that amount. So that would be our R value. That's the Lagrange error in those two calculations.